going to share screen. Okay, so I think today we should be able to complete the study of the examples for last class's contents. So it's about KNN. So K nearest neighbor. Okay, it's for classification. And it's unsupervised learning. The KNN, if you recall. And the two major factors that we need to consider is K is number of neighbors. And the other is distance. A distance, like we show there are some general Minkowski distance, is it? And then you can have a Euclidean distance or Manhattan distance. And so that's about KN. Last class, we also learned some general rules about data pre-processing. So last class, all we discussed about theoretical. Okay, so today we will take a look at the examples. So this first example is about KNN. Okay, so let's take a look. How are we going to use the KNN? Also from sklearn. Okay, and this example, the data set, it's about some breast cancer. Okay, from some Wisconsin region to collect the data. Okay, so we have the file, and it's also a comma separated file. So that's as normal. It's nothing different. And then what over here, the data, it has some question mark. So some of the data it may be missing as a question mark. So it's replace it. And also it's going to drop the ID because that's kind of doesn't have any effect to our data analysis. So here is a quick look of the first 5 records. Okay, about, so you can see there are a number of features, the columns. And also over here, we do some data type change, okay, as type. And for the features, so this is regarding features. And for the feature, we drop the class part. Class is like the cancer, yes or no, kind of positive or negative, etc. So we drop that, and all of the other features we keep. Okay, and the target is positive or negative, etc. for the cancer. Okay, and this part is also, as usual, we do test and train split, so nothing new. And then for KNN, is it? So you just call the KNN. Let's take a look at what are the neighbors. So for KNN, if you want to use, you also need to import these neighbors. Okay. And then from the neighbors, then you can create the KNN, the K nearest neighbor. So create that object. Then we just do fit and collect the accuracy score as usual. So nothing new here. And then for performance analysis, if you recall, that a lot of time, if you just use accuracy, it may not may not be able to provide enough information for you to identify the optimal model that you want to pick. So a lot of time we can collect some other information. If you recall, confusion matrix, it is one of that. And for sklearn, it also gives us a classification report and more detailed information about precision, recall, and that F score, that F1 score. So we can, so based on this, we do our prediction with the testing data, and for the testing data, then we collect, so this is on testing part from our model, okay? And then we collect the confusion matrix, and this is the classification report, okay? So there are more detailed information for us. Okay, and what is the next part try to show is how the number of neighbors. So number of neighbors impact is for this part. So we use a loop. Within the loop? So here you define the number of neighbors plug in. So from 1 to 40, etc. And then you fit you train the model, and then you do predict with the test data, and then what we measure is the real test target value and the predicted value, to see if they are not equal, then that means there is an error, okay? So with this loop, then we check the neighbors between 1 to 40, how it's going to impact. So we are going to collect the error rates. And then we do plot. Okay, so here we use a pie plot. So pie plot, we plot the error, against the number of neighbors. Okay. And from this plotting, then it can clearly help us to see that we can see between 1 to 10-ish, in this range, the number of neighbors impact the error rate a lot, but you can see kind of like after 10, especially like after 15, it's kind of the error rate almost goes to stable, So based on this kind of analysis, then you can kind of see, okay, the number of neighbors, if you choose like maybe 16-ish or 17, then it won't 16, 17-ish, and then the algorithm, the error rate is kind of reach to its stabilization state, So it's kind of, that's the optimal number of neighbors. So you can use this kind of technique to pick the best number of neighbors. Okay, and then what is the next part to try to show? If you recall, we also discussed, just touch a little bit of feature selection. And in machine learning, feature engineering is also a topic, a kind of a big topic, okay? And the feature selection is part of it. And feature selection, sometimes you have too many features, So, so how do we pick the optimal number of features that's going to contribute the most for the model, Because sometimes you don't want your model to be overfitting, or if too many features, then the training also converges slowly. So there are a number of factors we need to think about. And if you recall, when we discussed the decision tree and random forest, and they provide us something regarding feature importance results that we can collect, then that can help us to pick the optimal number of features. So for this example, so for this breast cancer data, we also try to run the random forest, okay? And here, this N estimator is number of trees, okay, number of trees. And then we fit the model, as it we train the model, then this is the testing part, okay. Then we can collect the score and also confusion and classification report, is it? So let's see. So regarding the same data set, this time we use random forest. So accuracy is about 97, is it? And precision and recall. And let's see for the KNN, it's 98%, and for random it's 97. So not a huge difference, is it? If we compare this to algorithm. And then let's see, how do we access feature importance, okay, from random forest? So that's sometimes can give us some more internal information. Okay, so we know the features of the columns of the data frame, they are all features. Yeah. Features, is it? And for random forest and decision tree, if you recall previously, we also saw it. It's a feature importance. Okay, so we can collect the feature importance directly after you train the model. Okay, and then we can use this arc sort function. Okay, to sort it. Okay, and here we want to arrange it in descending order. So that's why here we do the reverse array. Okay, and then we will be able to see, is it? So this arc sort is, you're going to get the importance is, it's a kind of like an array, is it? And then we can find, this is the feature index. So basically it's a column. Is this, so suppose this is 0, 1, 2, something, is it the index, column index. So after you do this arc sort with this feature importance, then we will get, so this is the most important, and the second most important, is it the indexes, so you know the feature importance. So after we have this data, that we know the data, and then we can also output. So this print is just output, the corresponding feature name and its percentage in the overall importance. Overall importance, if you add all of them together, it should be 1, is it? So it's kind of the ratio of this feature in the importance. Okay. So this one is the first one, is it? So that's in the original feature, it's also the first one. Okay, but the third one, this one, in the original feature column, in feature column, it is 5. Okay, it is 5. Okay, and the percentage it's taken. Okay. So that's regarding feature importance. And after you collect the feature importance, a lot of time, because for machine learning and data analytics, another major part is visualization. Is it? And for feature importance, if we do the bar plotting, and then it's very obvious for us to see, okay, what are the important features? Is it? So over here, we do the bar plotting regarding the feature importance, okay. So over here, it shows us, so visualization, then clearly you can see, okay, almost like kind of the top 1, 2, 3, 4, 5, 6, 7, 8. Is it maybe the top 8 takes most important role? Is it after that we can kind of ignore the remaining features because it's visualization? You can also clearly see the percentages they contribute, is it, to the features. Okay, and the visualization, decision tree, and a small tree, and this we already discussed. So after class, you can take a look to how to again to how to get the tree. Okay, and then what the next part is regarding the data pre-processing. Okay, data pre-processing is sometimes in your data you have some nav values, so null values. Is it, how are we going to handle them? And also sometimes for your feature is nominal data, if you recall. Is it, or ordinal data? And they are not numeric values. Is it? So we need to handle that. Is it? And sometimes maybe feature selection you should also consider. Okay, so over here anyway, so this just shows us some idea. Okay, so we have this kind of data. Is it within this data set you have some nav values? Is it? And normally after you have a data set, then you need to kind of do some check, is it, to see how many nav values you have, is it, so that you know it, how are you going to do the data pressing? Okay, not you get a data set, then you just directly apply machine learning model that sometimes may not get the good result. Okay. So overall, you have some idea about the data. Is it are there a lot of nav values? Are the data? Oh, another part is like a feature scaling. Is it? Feature scaling is, do we need to do like normalization or like a standardization? Is it so? And the normalization normally is you bring data to 0 to 1 range, is it? And standardization is regarding some data, the distribution, so that we bring the mean we bring the data into the mean of 0, is it? And the unit variance, okay. So then we know like how far away the data, 1 standard deviation or 2 standard deviations from the mean. So that's regarding feature scaling. Sometimes you need to do it, not always. Is it like for decision tree, then you don't need to do feature scaling. Okay, and if you recall previously when we learned Python and its package, we also learned like drop and A you can use. Is it, for drop and A you can specify along which axis is it you are going to drop the null values, the nav values. Is it, in this case it's remove for rows, okay? And you can also specify a long column, okay, a long column. And you can also specify only drop. So if you specify how as all, then what it means is drop when all columns or rows are net, then you're going to drop it. In this case, if you just have one, you're not going to drop it, okay? And you can also specify the threshold, is it? So as a drop row has less than, is it? You can specify the threshold. How are you going to drop? And what the next one show, you can also specify, is it a specific column? Is it like over here it shows? So even just with the drop NA, there are multiple options, okay, then we can do. And for sklearn, it also provides us a class that we can directly use from the imputer package. Okay, and be careful. The sklearn, they change. Okay, so now with the newer version, in the past it's just imputer. We don't need the simple imputer. Now they change. So there's some little change over here. Okay, so we need to be careful. For different version, you will see it's different. If you the sklearn package, okay. And over here, so we are going to use that simple imputer. Okay, for simple imputer, then you can specify the missing values net. Then how you are going to do it. If you recall previously in the theoretical part, we learned that not always drop. Is it? That's not a best strategy, is it? Sometimes we do interception, not intercept, interpolation. And one of the strategy to do the interpolation a lot is using mean values. Mean values to substitute the nav values. Okay, that's how this strategy comes from here. Okay, so sklearn, the simple imputer, can also help you deal with the net so that you don't need to do row by row, column by column handling, etc. And then you can just create a model, but you need to specify what kind of mean. You use minimum, maximum mean, or what kind of strategy, and also be careful. Its change with this simple imputer is when you call the fit, you need to do something like this. Okay, you need to do this simple parenthesis, then call that fit. Then you plug in the data set. Okay, then you want which you are going to deal those nav values. And after that, you're going to transform. But for the transform, so what this fit will return something to you, that then you are going to use that model to do the transformation for the values. Then you can see that for the nav values, we can do a comparison. Is that for the nav values here, the second row, column C, that it's replaced with 7.5. 7.5 is the mean of what? Is the mean of this two, etc. And then for this nav value, it's replaced with 6. 6 is mean value of this two, etc. So that's how this simple imputer can automatically help you a lot as that when you deal with the nav values. Okay, and then what the next one is about categorical data, is it nominal and ordinal? Is it ordinal itself has the order? Is it like medium size, large size, or X large? Is it they belong to ordinal? But for green, red, then they belong to nominal. Okay, so when we deal with these two, it's different. And also for class, is it? We also need to convert them to numeric values. Okay. So anyway, so here is we can clearly see that this original data set, if you want directly apply to machine learning, it won't work. Okay. So we need to convert all of this to numeric data first. And the one way for the conversion is you directly do the mapping. Yes, we can directly do the mapping. You create a dictionary, the Python dictionary. Okay. Python dictionary. Then you do the mapping that with the categorical value and the numeric value. Okay. Then you reassign the column. Is it reassign? Then you do the mapping with the dictionary. Is it? Then after that, you convert the size. Is it? Column to numeric value. Okay. So here is one approach. We borrow Python's dictionary. Okay. And after that, sometimes you may want to get it back to the ordinal data, is it to categorical data? You can still do that, is it? So over here, this is dictionary comprehension. The previously we learned list comprehension, dictionary comprehension. Here we use that, is it? So this is that dictionary, is it? And it's items. Then you loop through that, is it? And here you just reverse it, is it? Here is KV and here is VK, is it? And with a colon, okay? So here is how you can reverse it back, okay? After that, you do the mapping, then you can reverse it back, okay? So it's pretty flexible, okay, in this case. And what this part is try to show, if you recall, we have the class, is it? And we can also encoding the class labels, okay, from categorical to numeric, is it? So similar thing, but for the class, so this is that column of data, is it? Then you want to know the unique ones, is it? So NumPy unique, is it? And then we do enumeration, is it? Because when you do enumeration, it automatically generates the responding index. And this is a unique label, is it? Then we can reverse it, is it? So this is dictionary comprehension, is it? You create this class mapping, okay? So quite helpful. Okay, and then you can reassign this column. Then it's numeric values. And if you take a look now, this column it's still categorical data, is it? But green, red, blue, it's this is kind of, you know, this is not ordinal, they are nominal data, is it? So regarding this nominal data, how are we going to handle that? And of course, you can still do, so you can still do the mapping that we just did, is it? For this, this is regarding, this is still regarding the class label, okay? And you can also reverse back, okay? And then let's see. For the class label, we can also borrow sklearn's label encoder to do it. Okay, so with sklearn's data pre-processing the label encoder, you can just create the label encoder object and then you do fit transform. It can also help us do that. So label encoder also works. Okay, so just multiple ways we can do that. And then this time, let's come back to the color column. Color column? It's nominal feature. For nominal feature? Normally, what we use the technique is we call it one-hot encoding. Okay, because it's not like a shirt size. It has some order inherently. And for color, there is no which color is larger than the other color. There is no such thing, It's just if it is such color, just this kind of concept. So for one-hot encoder, it's basically yes or no. Is it yes or no? And one-hot encoding, then in this case is we have red, and we have green, and we have blue, like this. So then it's kind of you convert it to 3 color, three colors. Then for each color, if it is red, you encode it as 1. Otherwise, you encode it as 0. Something like this? So then the feature columns is going to be increased. So it's kind of you add more feature, but basically not. They are all regarding color. Okay, so that's what a one-hot encoding means for nominal data. Okay, and what over here it first to show us is do the label encoder. Label encoder for the color? Then you can see it's 1, 2, 0. That doesn't make a lot of sense for color. So then in this case, we can do one-hot encoder, okay, and you do pre-processing, import it, okay, import it. And the one-hot encoder from SK also changed, okay, updated. For the newer ones, it's not as convenient as the older version for some reason, okay. And for this one-hot encoder, we needed to create the object first, and then you do fit transform, okay. And then over here, we specify that color column, and its value also needed to be reshaped, okay, reshaped, and then convert to array, okay. And this is the result. This is the result. But you can see that over here, it's the result. Result only has the color. It doesn't have size and the purchase price or something other information. It only has color. Okay, the result. So if you wanted to get this back to the original, then in this case, you also need to do the data frame merging. Okay, you need to merge it to create a new data frame. Okay, so with this one-hot encoder, so just be careful. And but if you recall in Python, one-hot encoding can directly be done in pandas. There is a method called get dummies. Get dummies. For the get dummies, then automatically. But of course, it's regarding all of this are already numeric. So sometimes you may need to do multiple steps, okay? You cannot achieve in one step, you get everything done, okay? So it's multiple steps. So then in this case, if all other columns are already numeric, if you do the get dummies, it will take care of the color column. Then it will have 3 new column, and have 0 or 1. So this is also much convenient, okay? For get dummies, and if you take a close look, it looks like that color blue one dropped. Is it? Because sometimes we don't need that because that's multicollinear. Is it? So for get dummies, because if it is not green, if it is not red, like this case, then that means this item is blue inherently. Is it? So then you can enable this drop first. Okay, so then that's going to be dropped. Okay, so one hot encoder is it, and one hot encoder, and for the collinear, is it multi-collinear? You can also handle it. Is it handle it? Then just do some special a little trick. Okay, so that's regarding the nav values handling and nominal and ordinal, so categorical data, how are we going to handle? So there are multiple options, okay? So you can choose either using sklearns or use just Pythons, okay? What next one also try to show us is regarding some wine data analysis with KNN, okay? So we can see that there are also a lot of features. Is it? And total number of samples is not too large. It's just 178, okay? And give you some statistics regarding all of the data. So train test, is it split? So nothing new here. And over here, it also shows us you can also do the data scaling, is it? So this is normalization, min-max scalar, if you recall, that is do normalization. So you can choose, okay. And here you can also do standardization, okay. And remember, you need to apply it both on train and the test, okay. Because you apply the data to train the test, if you use a region, that won't work, okay. So just be careful. And the standardization, normalization. Okay, so what next try to show is how do we select meaningful features, feature selection, okay? And the feature selection, if you recall, previously we also discussed, is it L1 and L2 regularization? So keep this in mind. L1 regularization can also be applied to feature selection. Okay, L2, no, L2 is just to regularize. Okay, to try to penalize the weight. But L1, if you recall, it's because then if the intersection is it of the contour, then it's here, then the other feature is 0, is it? So this is W1, this is W2, then the other feature goes to 0. So that's how you can just think this feature plays more important role, okay? Okay, then let's see, how are we going to do this? So in sklearn, there is also some package help us do feature selection, is it? And over there is a model called select from model. So we can borrow this, okay? And select from model within it. Over here, we plug in logistic regression. Okay, and this is for L2 regularization, is it? And you can see L1 is on the penalization. Okay, it's on penalty. Okay, and over here we need to specify the solver. Okay, because the default one it doesn't work. Okay, in this case, because if you check the official documentation when you do the L1 penalization, the default solver won't work. Okay, so you need to change the solver. And then we can do the train. Okay, and after that, so this is from select from model. Okay, the select from model, then to give you a function called get support. Get support return you what? It's an array of Boolean values. These Boolean values will tell you about some feature. Okay, so if the value is true, that means the feature importance is greater than the mean importance. Okay, if false, that means it doesn't. It's less than the mean importance. Is it? So over here you can see the result. We have 3 that's less than the mean importance. This get support will give you this. It's quite helpful, is it? Then the corresponding feature, no, this you cannot skip. You cannot remove those features for your training. But for some of that you can, is it? And then over here, this is the respective coefficient. Basically, it's the weights. It's a weight, is it? And over here, because it's multi-class, is it? For multi-class, if you recall, we use that one versus the rest strategy. Is it for multi-class? That's how over here you have three batch of coefficient. Otherwise, you should only have 1 batch, is it? But over here, you have 3 batches because, okay, this is for the class 1, is it? This is class 2 and the class 3, something like this is class 1 versus the rest. This is class 2 versus the rest. Then class 3 versus the rest. Okay, so that's why we have this 3 batch, okay, 3 set. And then next just shows us how are we going to pick out all of the important features, is it? So from that get support, is it? You know which feature is important, then you can collect all of them, store them in a list, is it? So once again, here use list comprehension. Okay, and then you can get out the features based on this, is it? And over here, it just shows us, okay, and total feature, selected feature, is it? And we can also find the feature coefficient shrank to 0 once, is it? So all of those we can collect them. Okay, and what then this part is you can pick out the columns, is it? So pick out columns, not important. So feature not important, is it? So you can also do the arg where, is it? And if you recall that importance array, is it? Then we can choose that. So it's just multiple ways. And here you can also do something like this, okay? And then use the numpy where, okay, to find that. Then you can also collect the column index, okay? And this column just shows us all of the column, okay, of the column. And then what next we try to do is, and here we didn't reduce any of the features, okay, using original ones. And over here, this remove feature, they pick out the feature that's going to be removed, okay, the name of the feature. And then next, let's see. So this time we first applied logistic regression, is it? And we provide L1 penalty, and we also, the silver solver also need to be changed, is it? Then we train this model, okay, with logistic regression. And then we can see the accuracy is quite high, is it? And we also get interception, is it? And the coefficient. You can collect all of this data, okay? And what the next part to try to show us is over here, we use logistic regression, that, and we do the path. So here we try to see how this L2 regularization impact the weights, okay? Impact the weight. So with different regularization, and let's see how the weight is changed for this plotting, okay? And so this is a result of the plotting. So for this result of the plotting, you can see is it the larger the C is, the weight also value is large. Is it the smaller of the C, then the weight almost zero. Is it? That's why, because the C is small, then that means the bias influence is high. And bias influence is high, then it will suppress weights impact. Is it? So that's why the weights gets closing to zero. Is it? So that's not good. So how do we find the balance? Is it between the regularization and the optimal result? Is it? So that's we need to do the tuning. Okay, parameter tuning. So this is kind of also shows how part of the parameter tuning, so that you can pick the best C value. Okay, and sequential feature selection, and we didn't discuss it. Okay, so let's just because that's not from the sklearn. Okay, but if you want to use, you can go ahead to try to use it. Okay. And what the next part to try to show us is to show us this K3 basically is going to pick out some of the important features. Okay, so those are important features, 1, 2, 3, yeah, pick 3 important feature. And over here for this Y, we also try with KNN, okay, with training, and then we collect with the testing. Is it? So the result is not bad. Is it? So 96%-ish. This is on the original data set. Okay, so keep all of the features with all features. All features, is it? And what the next one, it try to do, if you take a look here, the fit, is it? And over here, the fit is not going to use all of the features. It's only going to use the features that's based on the previous selection result, is it? And then in this case, after we do the model training, and if we take a look at their accuracy, we can see it's also not too bad. Is it 90%-ish? Okay, and what the next one try to show is with random forest, we can also do feature importance. Is it? And previously we already saw, is it, in our previous discussion, then you can use the arc sort to sort your feature importance. Is it? Feature importance. And from the feature importance, And we can also do select model, if you recall. As a select model, you can also plug in with the random forest. And over here, you define the threshold. So you use the threshold value to do the feature selection. Feature selection here. Okay, so what this part shows is just feature whose importance is greater or equal than this threshold. Okay, otherwise you're not going to use it. Then in this case, then you can also say, okay, how many samples meet the criteria? Is it, and also to give you features that meet the criteria. Is, are those features? Is it? And with those features, and then if you do the model training, like with random forest, and then if you do testing, training and the testing, you can see sometimes with the testing, the training is pretty good, but the testing is not good. It's very bad. That, and when you apply to KNN, then you can also see the result. It's not bad. It's not good. That, so you can also see for the machine learning, a lot of tuning work we need to do. Okay. Okay, so that's all.